Welcome to Section 4 of Introduction to Image Processing. This section describes operations for transforming the histogram of an image and some common applications of those transformations. In many cases, it is useful to simply have a uniform histogram, where the pixels are evenly distributed across the range of possible values. As an example, here is an image where the pixel values are not evenly distributed, since most of the pixels in this image are light gray. Here is the histogram of that image, which is dominated by light gray pixels with values near 1. Here is that same image after spreading out the pixel values to get a more uniform histogram, which can be done in the Wolfram language using a function called histogram transform. The pixels in the resulting image are more evenly distributed across the range of possible shades of gray, which greatly enhances the contrast of the image. Transforming pixel values to get a uniform histogram is called histogram equalization. The effect of histogram equalization can also be seen in the image histogram. Here is the histogram for the equalized image showing a more uniform distribution of pixel values. A more quantitative way of characterizing the spread of pixel values beyond just looking at the histogram is to calculate statistical properties of the pixel values like the mean and the standard deviation. For example, for the low contrast image with pixel values concentrated near the upper end of the range, the mean is a number close to 1 because this is a fairly bright image, and the standard deviation is a small number because the spread of pixel values is not very big, as would be expected for an image with low contrast. In the Wolfram language, there is a built-in function called image measurements for giving these and other properties of an image. For example, this shows the image measurements function giving the mean and the standard deviation of the pixel values for this image. Those measurements can be compared with the same measurements after equalization, showing that the equalized pixel values have a mean close to 0.5 and a much larger standard deviation, which is what would be expected for a uniform distribution. A related transformation is histogram matching, which is used to transform the histogram of one image to match the histogram of another image or to match some predetermined histogram. For example, here is an image of an outdoor scene and a second image of approximately the same scene. The second image uses a much narrower range of shades of gray, such as might happen when images are captured with different devices or under different conditions. Here are the histograms for these images, showing that the second image uses a much narrower range of shades of gray. When comparing images, it is often easier to detect differences if the images use similar color schemes or a similar range of shades of gray. For example, this input uses the histogram transform function to transform the pixel values in the second image so that the histogram of the transformed image is similar to the histogram of the first image. The scene in the second image includes 3 birds in the sky. It is easier to detect those sorts of differences or to otherwise compare the images if the images at least have similar histograms. Histogram matching can also be useful when combining adjacent or overlapping images into a single image, a process sometimes called image stitching. For example, consider combining these two images showing the left and right sides of a scene. Putting these images next to each other reveals a distinct boundary between the images, since the image on the right is noticeably darker than the image on the left. Histogram matching provides one way of reducing or eliminating this type of boundary. For example, this uses the histogram transform function to transform the histogram of the image on the right to match the histogram of the image on the left. After histogram matching, the images can be combined and the boundary between the two images is nearly invisible. Histogram operations can also be used for color images by transforming each color channel separately. For example, starting with these two images, consider matching the histogram of the first image to match the histogram of the second image. The image to match is sometimes called the reference image. Histogram matching for these color images can be done using the histogram transform function, just as for grayscale images. The result is an image where the colors of the first image have been transformed so that the histogram of the transformed image matches as closely as possible the histogram of the reference image. That's the end of the examples for this section. To summarize, the examples included histogram equalization and histogram matching, and applications of those operations to contrast enhancement, comparing images, combining images, and color transfer. In the Wolfram language, histogram matching and histogram equalization can be done using the histogram transform function.